The history of science is full of happy accidents. Most of you have heard that penicillin was discovered in 1928 when a few mold spores landed on some neglected petri dishes in laboratory in London. But sometimes serendipity's role is a bit less. Henning Brandt was a German alchemist. In the 60s, he did marry first rich lady, and then after her death a second rich lady. And he used their money to literally try to make gold. Brandt was convinced he could distill gold from golden substance human urine. Do you remember the story final? He accidentally discovered phosphorus. Long before alchemy came into practice, gold was already the most valuable metal. It was a symbol of power and wealth and was a prize for its beauty. Gold has many of the most prized physical and chemical property. It is malleable, it is ductile, it does not tarnish, it is not damaged by heat, and it is considered to be imperishable. Since it was considered to be the most perfect metal, alchemists tried to transmute common, ordinary metals such as copper, iron, tin, lead into gold. Unfortunately, there is no one way that all alchemists follow in order to create gold. In fact, most alchemists never succeeded in creating gold at all. Many alchemists felt that mercury was the closest metal to gold. They may have been correct, since in 20th century 1960s physicists were able to create gold atom from mercury atoms. These metals are next to each other in the periodic table of elements. Gold has 79 protons, while mercury has 80. By knocking out a proton from the nuclei of mercury atoms, these modern physicists were able to create very small quantity of gold, thus proving that creating gold from another metal is possible. Of course, our modern alchemists created highly reactive atoms of gold, which only survived for a few moments before the atomic stability destroys them. How much gold is there in the world? The best estimates currently available suggest that around 200,000 tons of gold has been mined throughout history, of which around two-thirds has been mined since 1950. And since gold is virtually indestructible, this means that almost all of this metal is still around in the one form or another. If every single piece of this gold were placed next to each other, the resulting cube of pure gold would only measure around 21 meters of each side. The good news is that we are not likely to run out of gold anytime soon. The scientists estimate there are around 50,000 tons of mineable gold still in the ground, and more is likely to be discovered. The good news is that the way we use gold is starting to change. The gold is being used in the technology industry. Can gold be a catalyst? Gold has long been considered as inert, unreactive, a chemically uninteresting element. The technological application of gold were limited to its use as an electrical conductor and an inert coating. The situation changed radically in 21st century. Investigation performed in the last 20 years demonstrate the incredible wide use of gold in catalytic process. The work by Hutching was showed that gold is the best catalyst for the hydrochlorination of acetylene, and the study by Haruta, who investigates the oxidation of carbon monoxide on gold nanoparticles at low temperature. Those publications were a publication which have changed view on this noble metal. In the past decade, the field of application of gold-containing catalysts extended. This was accompanied by explosive growth in publications. Only small gold nanoparticles can effectively activate oxygen. The global catalyst market size was valued at $44 billion in 2090s, and it is expected to grow at a compound annual growth rate of 4.4% from 2020 to 2027. What do you prefer, mine the gold or develop new catalysts? Solid catalysts dominate at industrial catalysis. In view of the large-scale applications such as in ammonia synthesis for fertilizers, oil refinery for transportation fuel, petrochemicals, and environmental catalysis. The most important class of solid catalysts are the so-called supported catalysts that often contain of supports such as aluminum or silica. The active nanoparticle of this catalyst can be metal, metal oxide, or metal sulfide with size of 1 till 20 nanometers. Besides oxide, carbon-supported catalysts are relevant, in particular for liquid phase processes. The bulk catalysts contain mainly the active component by mass, with electronic and structural promoters. The iron-based ammonia synthesis catalyst, for example, the halide are widely applied as well in many oil refinery and petrochemical application. The process of catalyst synthesis also denoted to as a catalyst preparation and manufacture involve control of the composition and structure of the solid to attain at the desired performance, namely activity, selectivity, and stability. To get this performance, we need to realize the desired nature, density, and accessibility of the active sites. All three aspects affect on the performance and should be controlled during the synthesis. The nature of the active site has a direct behavior on the activity and selectivity and will be determined by atomic structure. For acid site in the halide, the nature and geometry of the heteroatoms, for example, it can be aluminum silica, will determine acid strength. The density of the acid site, which is important first of all for activity, may be controlled by the metal loading or by the alumina-silica ratio of the halides. However, this ratio will also affect for acid strength. Accessibility of active sites demands control of porosity. Porosity of the solid catalyst is the key for the rate of mass transfer of reactants to and products from the active sites that can be affect activity via diffusion rate and selectivity because of extent of secondary reaction and stability via coke formation. Depending on the application, microscopic catalyst bodies differ in size and shape. For fluidized bed application, the size is in the range of tens of micrometers, where fixed bed application require millimeter-sized particles. A typical structure for a cylindrical shaped catalyst for fixed bed application is shown in the slides. This figure also shows the multiple length scale involved in solid catalyst. The microscopic scales involve the structure of the active sites. The mesoscopic scale, the pore system, and the size of support particles, as well as the particles of the active phase. The importance of the microscopic scales goes without saying, as it is determine the intrinsic activity and selectivity of the catalyst. The mesoscopic length scale affect, among other, the interparticle mass transfer of the catalyst. The microscopic size and shape is relevant for properties such as a pressure drop in fixed bed reactor, mechanical strength, and attrition resistance. The development of the manufacture of solid catalyst synthesis is summarized in the table. The first solid catalyst contain of supports an active phase available from nature. Bauxite and clays are examples of active phase, while, for example, Kesselgur is a natural source of silica support material. Using salt gel chemistry have been developed synthesis support materials. Application technique for the active phase based on impregnation and drying development during the 20th century. Hydrothermal synthesis can be important for synthetic zeolites such as ZSM5. Using micelle templating, nanostructural silica MCM41 and SBA15 and other oxides have been produced during the last 20 years. Using chemical vapor deposition technique, nanostructured carbon materials such as a carbon nanofiber and carbon nanotube have been produced and explored as a catalyst support. The slide presents three generations of support materials, that is natural silica, Kesselgur, silica gel, and odorate mesoporous silica. Moving from natural to synthetic materials has a great improvement the controls over composition and texture of the support. The choice of a suitable preparation method and preparation condition is very critical. The most widely applied method both in industry and academia is impregnation and drying method. In this method, 4 distinct steps can be described as schematically shown in a figure. Each of these elementary steps has a large impact on the final catalyst, in particular for the distribution of the dispersion and the distribution of the active metal nanoparticles on the support. So-called incipient wetness impregnation, sometimes called dry impregnation or pore volume impregnation, involve contacting the support with an amount of the solution of the precursor of the active phase such that the pore will just be filled. The pore volume of the support can be determined by nitrogen chemisorption or water uptake measurement. If we use more solution than the pore volume, the method is referred to as a wet impregnation. First, we consider whether or not the solution will enter the pores of the support, which is a matter of wetting. For hydrophilic materials, pore filling will be fast. However, if support is hydrophobic, then the capillary pressure is negative and an external pressure has to be applied to force the liquid into the pores. A typical example of hydrophobic support is carbon. Oxidic support are usually hydrophilic, but these depend on the concentration of hydroxyl group on the surface of the oxide nanoparticles. In case of hydrophobicity, it is advised to use a less polar solvent such as ethanol or isopropanol. The disadvantage in this that the maximum concentration of the metal precursor is usually lower as these solvents. Impregnation is followed by drying. Okay. If strong interaction between the precursor species in solvent and the support prevail, it is expected that the distribution over the support will not change much upon drying. In case the interactions are weak, extensive redistribution may occur. In addition, if the drying process is not carried out carefully, the catalytically active materials may become concentrated at the mouth of the pores, or may even move onto the outer surface of the support. After impregnation and drying, the catalyst precursor is usually calcine, that is, heated in air. Calcination, or more general thermal treatment, is carried out to decompose the metal salts and to convert the metal salt into metal oxide. Depending on the nature of the nanoparticles required for the catalysis, further activation step may be needed. In the case of metallic nanoparticles, hydrogen reduction step is convert the metal oxide into metal. More often hydrogen used as a reductant. Critical parameters may be involved the concentration of hydrogen, the pressure and the space velocity and the temperature ramp. In case in point that has been studied extensively is reduction of cobalt oxide, dispersed on different support and under different conditions. The relevance of this example is related to Fischer-Tropsch synthesis, for which metallic cobalt nanoparticles are active. Since cobalt oxide can form mixed compound with oxidic support, for example it can be cobalt aluminate, cobalt silicates or cobalt titanates, their reducibility may be different. In particular, the two-step reduction cobalt 304 to cobalt O and to metallic cobalt is relevant in this respect. Usually the first step is facile, but second step is slow because of strong interaction of mixed compound formation between cobalt O and the support.
Today we're going to look at one of the most traditional catalyst synthesis techniques. We will look at incipient wetness impregnation, and we will also look at wet impregnation, and we will learn the difference between both. To begin with, you'll need to find your support. That is the carrier of your active metal or your active species that will catalyze the reaction. In this case, today I'm going to be preparing a nickel catalyst that is supported on gamma alumina. So the support in this case is gamma alumina. It's a white powder. And I have made sure that I have crushed this support into fine powder. This will limit mass transfer during the synthesis procedure. The incipient wetness impregnation requires us to use a solution that contains the active metal to fill up the pores of this carrier. And so, in order to have proper dry or incipient wetness impregnation, you must match the pore volume of the sample to the amount of solution that will be added. So first things first, we will titrate the gamma alumina support with some deionized water in order to find out the pore volume. Over here I have a pipette. I have some deionized water. And I have a sample that I have pre-weighed before starting this. And so I will slowly start to add drops of deionized water while mixing the mixture, and I will only stop when the entire sample is wet. Remember, we do not want the sample to be suspended in water. We just want to fill the pores. And so a little bit more. Push down. Nearly there. Perhaps a few more drops. Yeah. After mixing, you can already see that my fine powder is completely wet. However, there is no excess liquid around it. Having measured both the amount of water I've added into this crucible and the amount of starting support, I can easily calculate the pore volume. Let me check. So I've used half a gram of gamma alumina, and I've needed around 0.65 milliliters, which means the pore volume of this support I'm working with is 1.3 milliliters per gram. In the next step, we prepare our catalyst. So in here, I've dissolved a specific amount of my nickel precursor. In this case, I'm using nickel nitrate hexahydrate. The amount will correspond to the number of moles of nickel I would like to deposit on this sample. I've dissolved this amount of nickel in a specific amount of deionized water that corresponds to the pore volume of my sample, of my carrier over here. And so when I mix these two together, we should end up with something very similar to what we had at the beginning when we titrated the carrier. So here I have half a gram of gamma alumina and 0.65 milliliters of a solution containing nickel. Now I will slowly add the solution to the support while mixing at the same time. And now that I have completed the mixing, you can see that the entire support is wet. However, it is not suspended in any liquid. The color has also changed from white to a very light green hue. Now that we have our nickel nitrate dissolved, filling up the pores of our support, it's time to dry the sample. Usually samples are dried anywhere between 80 and 120 degrees, and that's just to remove the very last remaining amounts of water. After that, we perform a calcination step at a slightly higher temperature to remove and decompose the nitrate so that we are left with nickel oxide only on the support. And then the final step would be to reduce and activate the catalyst, reducing the nickel oxide to its metallic phase, which is the active species in this case. The calcination will be performed at 500 degrees, and that's sufficient to decompose the nitrate and give us a final nickel oxide phase on the support. And this is the nickel precursor we're using, a salt, a nitrate salt of nickel.
The most common type of impregnations can be classified in this table. All of you familiar with the first two, and those methods will be distinguished from the method referred to here as a strong electrostatic adsorption. The challenge of supported metal catalyst preparation is how to prepare the smallest, most stable metal particles by the simplest and cheapest method. From the fundamental point of view, the challenge of the catalyst preparation is to understand the mechanism of the process. With sufficient understanding, the art of catalyst preparation may be turned into a science. The metal oxide surface are commonly terminated by hydroxyl groups. Depending on metal oxide lattice structure, the detail bonding, the OH group are acidic, neutral, or basic. Using infrared spectroscopy, it can be confirmed that OH group are present at the surface of, for example, gamma alumina, which can be considered as a basic if OH group bonded to one alumina, neutral OH group bonded to two aluminas, or acidic bridged OH bonding to three alumina. Similar statement can be made for other oxide surfaces. The reported density OH group on oxide surfaces typically are 5 OH per square nanometer for silica and around 8 OH per square nanometer for high surface area alumina. At low pH, the hydroxyl group will pick up a proton from the solution and become positively charged. At elevated pH, deprotonation of OH group will give rise to negative charge. The pH at which the net charge of dispersed oxide particles is zero is referred as a point of zero charge. Point of zero charge values for common support materials are listed in table. As indicated on figure, at pH less than point of zero charge, anion adsorption prevails. Where at pH more than point of zero charge, cation adsorption is dominant. The method is particularly attractive for deposition of the expensive noble metals such as rhodium, platinum, or palladium. Ion adsorption is carried out by contacting the support particles, it can be powder or bodies, with a large excess of diluted solution of your metal precursor. After proper equilibration, which is important when you use millimeter-sized support bodies, the loaded support is washed to remove non-adsorbed species and then dried. It is very important to do careful selection of the pH of solution with respect to the point of zero charge of your specific support in combination with the charge of the metal ions in solution. The adsorbed amount of platinum on silica and alumina as function of pH shown in this figure. For silica, the platinum tetraamine ions adsorb only extensively when above the point of zero charge of about 4. The maximum uptake of the silica amount to 6% of platinum, and the maximum uptake for silica is 0.8 micromole platinum per square nanometer. Can be attributed, and this can be attributed to the effective surface area of the platinum cation of 2 square nanometer per complex. From the figure also shows that cation adsorption on alumina is not very extensive, and anion adsorption is used more often. Typically with alumina, platinum chloric acid are used. To achieve strong electrostatic adsorption over catalyst support, attention must be paid to achieve the optimal value of pH. The dramatic effect of catalyst support surface on solution pH was first demonstrated in the method called mass titration. If a sufficient amount of oxide is placed into solution, the pH arrives at the point of zero charge for this oxide, at which point no driving force to proton transfer exists. This method can also be applied to supported oxide as illustrated in figure. Since niobium has a very acidic point of zero charge and alumina a basic one, there exists a wide pH range over which the respective oxide carry opposite charge. Between the pH value of 2 and 8, the niobium surface will be negatively charged and the alumina positively charged. If niobium is considered the promote phase and it is desired to have the promoter in close proximity of platinum site, the cationic precursor could be chosen and it should be adsorbed selectively on the niobium phase. Co-precipitation method is a method where one or more metals are precipitated together with a support or its precursor. This method is often considered to be more difficult and require an accurate control of condition and more complicated equipment. All catalyst features, surface area of the active phase, pore structure, particle size and shape are strongly dependent on the process condition, like the nature of the method dosing of ingredient, mixing and stirring. These conditions have to be accurately controlled throughout the precipitation process. A complication is that probably no single condition exists that is optimal for all of the above processes. A benefit of co-precipitation over impregnation is the high attainable metal loading of up to 80% or even higher, compared to typically less than 38% metal loading for impregnation. Because of this high metal loading, co-precipitated catalysts are often referred to as a bulk catalyst or self-supported catalyst. A drawback of the co-precipitation process is generation of large quantity of salt solution and the fact that after precipitation the product has to be separated, which is mostly done by filtration. Co-precipitated powders can be shaped, but after shaping, a calcination has to be applied to achieve mechanical strength. The materials have to be heated up to 700 or higher. Basic principles of precipitation. The solubility product constant KSP is the equilibrium constant for the solid substance dissolving in an aqua solution. It represents the level at which the solid dissolves in solution. The more soluble a substance is, the higher the KSP value it has. Consider the general dissolving reaction. To solve for KSP, it is necessary to take the molarity or concentration of the products and multiply them. If they are coefficient in front of any of the products, it is necessary to raise the product to that coefficient power. Note that the reactant A is not included in the KSP reaction. Solids are not included when calculated equilibrium constant expression because their concentration do not change the expression. Any change in their concentration are insignificant and therefore omitted. KSP represents the maximum extent that a solid that can dissolve in solution. Let's do exercises. What pH is required to just precipitate iron 3 hydroxide from a 0.1 molar iron chloride solution? We see that iron 3 hydroxide precipitate in acid solution when the pH just exceeds 1.8. When you precipitate a solution of iron chloride in water, it will surely hydrolyze to form iron 3 hydroxide, a rust chloride precipitate. To stabilize the iron 3 solution, you must acidify the solution, which, for example, hydrochloric acid. Note that precipitation generally will not be exactly at the calculated pH, as supersaturation is needed. The preparation of co-precipitated catalyst comprises a number of steps. For example, precipitation, filtration, washing, shaping, drying, calcination, and sometimes activation. During those steps, the basic properties of the catalyst are established. Precipitation includes three major steps, that is liquid mixing, nucleation, and crystal growth to form primary particles and aggregation of the primary particles. The process mostly starts with the formation of clusters, which are capable of spontaneous growth by the subsequent addition of monomers until a critical size is reached. Clusters smaller than this size tend to redissolve in solution, while large cluster will continue to grow. A nucleus has been compared to a chemical reaction, and activation barrier for this chemical reaction must be overcome. Therefore, it is necessary to create some degree of supersaturation before spontaneous crystallization will occur. it is evident that nucleation strongly depends on both concentration and temperature. If the nucleation rate is plotted as a function of supersaturation, a curve like on a slide is proceed. Thus, there is an essential critical supersaturation concentration below which nucleation is very slow and above which nucleation is very fast. The range between this critical supersaturation concentration and the solubility concentration is a domain of deposit precipitation, while impregnation is performed in the concentration range below the solubility limit. Especially for a multi-component system, it is important to operate at high supersaturation level so that the solubility product of all product is simultaneously exceeded. Supersaturation can be proceed in variety of ways. For example, cooling of the reaction mixture, evaporation of solvent, etc. Water is chosen as a solvent not only for economic reason, but mainly because solubility of most metal salts is much higher in water than in organic solvents. The solution on the movie was formed by dissolving around 160 grams of salt in 100 milliliters of water at close to 100 degrees, and then slowly cooling it to 20 degrees, to room temperature. Because the solubility of sodium acetate in water at 20 degrees is only like 46 grams per 100 milliliter of water, the solution is supersaturated. There are several co-precipitation modes of operation. In a batch-wise operation, the base can be added to the acid metal solution or vice versa, or both solutions can be added simultaneously. In a batch-wise operation, the product form at the beginning of the precipitation is different from the product form at the end of the process. Based on the solubility constant of the hydroxide, the following order of precipitation can be expected: iron, chromium, copper, zinc, nickel. This method can be lead to a mixture of product not only different in chemical composition but also with different structure and texture properties. To minimize the formation of mixed products, the preferred method is to operate at constant pH by using a simultaneously addition of reactants. However, even use this mode, mixture are produced because the change in liquid volume in the reactor change both the concentration of the reactants and hydrodynamics. A further improvement is to perform the process continuously.
So I will start with the salt solution. This contains both the nickel nitrate and the aluminum nitrate, both of which we will be precipitating. And in the other This is the ammonium hydroxide solution. Ml. We'll start stirring. I've placed deionized water in here as a buffer solution to start pH at 7. Now the heating is on. This is the heating power. And the temperature will be controlled and set to 30 degrees. Now that everything is ready, I will start to drop both solutions into the beaker. And the rates of addition need to be controlled so that the pH is higher than 7. In this case, we are aiming for a pH of 9 for the precipitation. You can always use pH paper to check whether the pH is at the value you require. You can already see some precipitation taking place. Okay, this is not an accurate measurement. Try another one. Oh, weird. Something wrong with this pH paper? Oh. And indeed, this indicates that the pH is around 9. This means that the rate at which we are adding both solutions is acceptable, and every few minutes it's advised to check the pH again, make sure that it's controlled. And as the liquid fills up the beaker, we'll probably need to increase the stirring rate. Have been added into the beaker. We will now keep this solution at 30 degrees for 12 hours so that we can age it. And so the next steps after this would be to out the precipitated particles, washing them until they are at a pH of 7, indicating that we have removed most of the ammonium ions, and then finally drying and calcining them.
The method of deposition precipitation is a modification of the precipitation methods in solution. It consists of the conversion of highly soluble metal precursor onto a support and not in solution. And the conversion into support and then into the precipitate is usually can be achieved by raising the pH of the solution. And to perform the precipitation exclusively on the surface of our support, two conditions must be fulfilled. First, interaction between the soluble metal precursor and the surface of the support is required. In such a case, the supersaturation curve assessed in the figure is shifted towards a lower concentration in the presence of support, curve assessed support. And second, the concentration of the precursor must be maintained between the concentrations of the saturation and the supersaturation curves to avoid the precipitation in solution. The key point for successful deposition precipitation is the gradual addition of the precipitating agent to avoid local rise of concentration above the supersaturation curve, which would cause of rapid nucleation of the precipitate in solution. The interaction with the support decreases the nucleation barrier, so at concentration between those of the supersaturation curve SS support and SS, the compound exclusively precipitate onto the support surface. In principle, this method of precipitation enables the deposition of a controlled amount of metal precursor up to high loading, and the interaction between the metal precursor and the support leads to the formation of highly dispersed active phase after thermal treatment. In practice, the support is suspended into the solution containing soluble precursor. The suspension is stirred, then the precipitation agent is added. After a given time of gradual and controlled addition of the precipitation agent, the solid sample is collected, washed, dry, and activated. As mentioned above, rising the pH is the most common way to perform deposition precipitation. It is better if the mixing and generation of the precipitant can be carried out separately. At the laboratory scale, this is possible with urea. This is a delay base which permits mixed and basification in two separate steps. A first step, mixing at room temperature, and the basification when the mixture is heated above 60 degrees, leading to urea hydrolysis, and this is lead to gradual rise of pH. As the deposition precipitation method using a base has been applied for the precipitation of various catalysts. The mechanism of deposition precipitation can be explained at a molecular level as shown on the figure on the slide. At the beginning of the basification of the solution, silica is negatively charged and exhibit cation adsorption capacity because pH is higher than its point of zero charge. For silica, a point of zero charge is equal to. And the first step of deposition precipitation is probably an electrostatic adsorption of the nickel hexa aqua complexes on the silica surface. The nickel hydroxo aqua complexes close to the silica surface can react with the silanol groups via hydrolytic adsorption. This is a reaction of heterocondensation between COH and nickel OH, which is lead to the formation of CO nickel bonds. Moreover, the nickel hydroxo aqua complexes can also react with each other via alation reaction and form brucitic layers of octahedral nickel bonded to the silica surface. It can be noted that the brucitic layer of nickel bonding to silica act as nuclear for the growing of support. It can be noted that brucitic layer of nickel bonded to silica act as a nuclear for the growth of supported nickel ferrosilicate or supported nickel hydroxide. What makes the difference between research catalyst sample and industrial catalyst? Obviously, industrial catalysts are shaped body which appearance varying from tiny fluidous bed shape up to large monolithic block, and they are manufactured on a large scale. Pelleting is a high pressure agglomeration technique producing particles. Usually this is short cylinders which high shape accuracy. Typically the dry catalyst powder is compressed by applying force up to 80 kN with a punching tool. Binders may be added to enhance the mechanical stability after material compression, and the important process parameter are the maximum pressure and the rate of pressure rise, both of which influence not only for hardness of the pellet produced but also the integrity of the particles inside. The process may cause crushing of crystals, shifting of crystal planes, and other effects of high mechanical stress. The further disadvantage of pelleting, its porosity and pore texture of the final product can hardly be controlled, and the figure shows that it is possible to press catalyst pellet with structured perforation such that mass transfer of reactants and product can proceed. Granulation is a size enlargement by weight trembling growth agglomeration. A cohesive liquid is sprayed onto the catalyst powder such that the weighted particles stick together. The granulation grows by contacting further particles like a rolling snowball. Extrusion is the most widely used technique for the shaping of fixed bed catalysts or carriers. The principle looks simple. A highly filled suspension or paste is passed through profile channels that determine the shape. A high pressure may be required for transport and deformation of this paste, and other than in pelleting, the effect of extrusion pressure is smaller. And one of the great advantages of extrusion is the flexibility with respect to the porosity of the finished product. Through adjustment of the liquid-solid ratio in extrusion paste, it is possible to vary the porosity between about 30 to and 60%. A widely used preparation route for metal oxide nanoparticles is via a gas phase reaction, for which the product is often called fumed. The process involves reacting of metal oxide precursor at high temperature with water or oxygen, as illustrated on a figure. As a precursor, often use a metal chloride, and temperature typically varied from 1000 till 1500. A small cluster are formed which then aggregate into the large unit with the porosity of the material represented by the space between the primary particles. The flame hydrolysis is used on a large industrial scale to produce high surface area metal oxide powder with very high purity. Different type of oxide can be produced. It can be silicon oxide, aluminum oxide, titanium or zirconium oxide. And one of the oldest example is so-called aerosil process, which is based on silicon tetrachloride precursor. This precursor is converted into silicon dioxide, typically at 1000 degrees, and it reacts with water that is formed in situ by reaction between hydrogen and oxygen. Alumina is very relevant catalyst support as the high surface area gamma or nu phases, as well as a crystalline alpha alumina corundum phase. Alumina oxide is produced on the large scale from the mineral bauxite by the Bayer process, which involves selective precipitation. High surface area alumina oxide can be prepared hydrothermally from aqua solution as well as via flame hydrolysis. The aqua solution chemistry of alumina is very rich. Alumina oxide is an amphoteric oxide which has a minimum solubility at pH 5.8. It's dissolving in both acidic solution and in alkaline solution. The phase formation upon neutralization of aqua solution is complex with the phase and composition depending on aging time, temperature, concentration, and contamination. Precipitation from acidic solution generally yield less ordered precipitate than from alkaline solution, and existence 3 polymorphous crystallite phase of alumina hydroxide upon aging bayrite and hapsides can be formed if aging at 80 degrees. Crystalline biamide is the dominant phase. Gibbsite is abundant in nature and formed directly by slow precipitation from acidic solution. Bayrite can be precipitated rapidly from solution with a pH above 5.8. The choice or either a silica or alumina support depend on the specific application and the metals that will be deposited. Silica has a low point of zero charge and it is difficult to deposit metals like gold. Alumina generally has the highest mechanical robustness as well as the highest thermal stability, especially when heat in the presence of steam. However, especially in case of gamma alumina, it does show a highest reactivity with a certain metal, especially bivalent metal cations that can easily be inserted into empty octahedral position in the structure. I have a homework for you. I would like that you write a 2-page text about the salt gel process as one of the roles for preparation of porous materials. Catalyst performance, activity, selectivity and stability is largely determined by their preparation. In this respect, catalyst synthesis may be considered as one of the most influential unit operations in industry, as this lecture provided an introduction to basic concepts and research tools relevant to catalyst synthesis. Thank you for your attention.